All right, so it's Sunday, 11:27 for our online office hour. I had one question already. So I did say you could turn in homework number 9 on Tuesday at noon in my office. So you can either turn it in tomorrow or Tuesday at noon. Okay, so you guys hearing me okay? Okay, good. So Jacob's got me. Clovis is there. Okay. All right, good. What other questions do you guys have? Okay, so um, if we take a look at this one, right, then for that first one, you have to, there's kind of two ways, right, that we can do it to figure out. The big part is figuring out really the H dot, right? So it's really all about how are you going to set your capital omega axis. So let's see if I can start out here, right? So I'm going to actually skip the figure that you can do out your, the first thing you want to do, of course, is your FBD and your KD, right? So I'm going to assume that you guys could get that one okay, where you're just going to end up drawing some forces and moments in at that point O. Okay, then the harder part, I think, if you do like a sum of moments about point O, is then you can equal your H, right, your total H dot about O. And so for this one, you've got to decide, what the full way you're going to do. And HO here is also going to be HG. So we're going to do our H dot about the little XYZ, and then we're going to add it to our capital omega crossed into our H of G. And then if we had it, we would also have to end up doing this, kind of G, but now it's G to G, right? Because we're doing it, we're really, like O to G times MAG. But since we're doing it about that center point, that's just going to go to 0. Okay, so now what we do is, for this one, let's say if we decided to just make, and I posted a couple of times different ways that you can work it by setting your omega. So if we just set our omega equal to the omega 2, right? So remember, we cannot just set it equal to omega 1. Our two choices are either to set it equal to omega 2 or to set it equal to both omega 2 and omega 1. So if we just set it equal to omega 2, okay, as we're going around, then basically it means that the only way this term is going to have a value is if it is increasing any type of the angular velocities, right? So does either omega 1 or omega 2 increase its speed? Okay, so that answer is no for that. Okay, so and then the other thing, Clovis, maybe I could just actually answer it from right up here. Did you note that the IXX and the IYY amounts here? Okay, so you did see that. Okay, so then as you're going through for this one, then what we want to do, we've got the capital omega equals omega 2. So now we can work it out and say, well, then we have this omega, when we work through it, it's going to be an omega 2, right? Oops, sorry, omega 2, and that's in which direction? Yep, so that's going to be in our positive K, and now we can cross this into, because that's the only one that's making things change direction. Right now we're going to have our, right, we have principal axes. Does that make sense here that we've got the principal axes here? Okay, and then what is the overall HG, right? So this is just going to be HG now. So what am I going to put in for my omegas for the HG term? Yeah, so the omega 1 is in the, right, it's going to be in the minus I hat direction, and the omega 2 is in the positive K hat, just like what we did before. Okay, so when we do this one out then, right, we're going to end up basically your K's are going to cancel out, right? When I do a K cross K, so then you're going to have it just end up being an IXX term, right? So IXX is just going to be the MR squared. Because basically, right, if I look here at this X, Y, Z, right, then I've got one plane of symmetry is XZ, another plane of symmetry is XY, right? So that O is going right through the center of the disk. Yeah, so you end up setting that, Clovis, remember? So you get to say which axis you're kind of riding along with. So if you do it with just the omega 2, then you're sitting here and you're going around with this. So it's like you're standing right on this thing here and you're going around just with the omega 2. The omega 1 direction is still, because you're rotating around with it, right? So that's the direction that this thing's always pointing. So you're going along with it, so that direction's not changing. That H is not changing with respect to you riding along on it. Okay? So we talked about in class where if you had chosen, right, the other thing you could have done is if you had chosen this capital omega to equal both of them together, right, then what happens is that this H dot G XYZ term is not equal to 0. Okay, and what you have to do there is then find out what your overall kind of omega dot's going to be. You remember us going over that? Because now you're basically, when you do that H dot G type of term, you're going to have some values here, here, and here. And we got the same thing no matter which way we worked it. Do you remember doing that, Clovis, last day? Okay, so look, I posted some solutions on there, and I worked it both ways. So there's maybe 2 or 3 different ones I think that I worked in both ways that are posted. Okay, so you get to choose one or the other. If you choose the one to just be omega 2, then the local one, the local frame here, this one right there, goes to 0. If you choose it to be both of them, like what I was saying right here, then it's not 0, because then you're going to have to do, like, omega 2 makes omega 1 change direction. Really what you're saying is omega 2 makes that H change direction. Yeah, I agree with you, Alex. So, when you have something like this, where, remember the big thing is when you choose that. And, hey, Aladai, can you mute yours? Thanks. I was just getting a little feedback. So, no worries. I thought I put some of my solutions, just they'd say like solutions to in-class problems that are worked on there. So I'll double check, but I was pretty sure I copied some stuff in from, like lessons 23 and 24. And I think there's also some, are those there, Eli, or not? I thought I did that. But I'll double check after we finish this too. So there was one question, Alec is saying, yeah, better ways to do it. So it's usually a little easier, I think, to do it this way. But the problem is, remember how we talked about if it's like a rectangle. So the reason that we're okay setting it equal to omega 2 here and just rotating it is because, and not rotating with the whole disk, is remember that if I'm just using, let's say, these red axes that aren't rotating with the disk as well, right? So this XYZ, even after this disk has rotated, around, let's say it's rotated around 20 degrees, right? It has this same moment of inertia matrix, remember, because the disk doesn't care, it's so symmetric that no matter how that thing's rotated, with respect to that XYZ, it's still going to be this, like the IXX is still mr squared, and the IYY is still 1/2 mr squared, no matter how much it's rotated. Does that make sense to you? Because no matter, so let's say, even if that thing's rotated 90 degrees, it still has the same, shape. Okay, and so let me contrast that to what if it was a rectangle, right? So right now, then if I'm using this kind of, this y direction, if it's going there, then it should make sense to you that that is different than this mass moment of inertia. Does that make sense to everybody? So if you have a shape that's not symmetric, like this rectangle, then you have to set your omega equal to both of them. So for this, you have to do omega equals omega 1 plus omega 2 if you had some sort of weird shape that's not symmetric like this. Okay, because otherwise your inertia tensor would change with time. You'd have to calculate it for every different angle. Does that make sense to you, Alec? Yeah, you would find that non-zero Hg dot, like Aladad saying. Yep, you would do, and basically that's not too big a deal, right? That just goes back to what we did before, where now we're going to say this is going to be the alpha is, omega 2 crossed into omega 1. Right? I mean, and you would also have plus an omega 1 dot in the minus x direction, right? But remember that went to 0, and then you'd have plus an omega 2 dot in the k direction, but that went to 0. Okay, more questions.
This is wild.
Yeah, so someone was asking about problem 5, and let's see. Is that the MATLAB one? The ball on the right. Okay, yep. Let me go down through here. So we got page, this one here, right? Okay, so if we look at here, right, then if we want to look at sort of that bar, right, it's got a that angle is 30 degrees there, right? So like some of these different problems, there's a couple ways you could try to solve it. So you could go through and do, see if you could figure out like an I. Well, first of all, what's about its G right here, right? So you could call this thing, right? This is what's probably going to be the most problem for you, right? So this could be either a Y prime, Z prime, right? So and there I'm doing it about its own, its own G there, right? So if I looked at just the bar there that's on that right-hand side, what of the products of inertia would any of those be non-zero? If I have like an x prime, y prime, z prime, right? So this direction would be the x prime. Would any of my products of inertia be non-zero? So Katie, I think you're saying which ones are 0, right? Yeah, so Katie's correct, right? Because really the y prime, z prime is a plane of symmetry, right? So the y prime z prime is a plane of symmetry. So the I x prime y prime would be 0, and the I x prime z prime would be 0. Okay, and then we'd have to go through that kind of integration type of deal to figure out what it is there. So it gets to be a little bit of a pain, right? So what's the other type of strategy we might be able to take? Yeah, so we could use sort of different axes, right? So instead of doing the axes we're shown here, why don't we consider instead using a different set of axes, right? So, and ones that would be principal. So I'm going to kind of get rid of this guy and this guy for a second, and we can kind of get rid of the red there. Why don't we make them principal axes by rotating, like what both Aladad and Alec and Katie are all suggesting, right? So now we're going to have principal axes, and you can rotate them whichever way you want, right? So let's say we're going to do then, hold on for a second, let me get that guy back. So you can decide if you want to rotate them, kind of somebody said they wanted to make Z perpendicular, right? So if we did that, then now this is going to be kind of a Z prime, and then this is going to be now like a Y prime. Okay, so now we're dealing with these axes, right? And it really doesn't matter too much to the sphere which way you do it, right? Those axes are going to really be the same. So if I do that, then what else ends up changing? What's the other thing I've ended up doing? Right, so I'm changing my inertial matrix now so that I have basically principal axes, but what else do I have to worry about? Yeah, so I'm going to have to put the omega into components now. Does that make okay sense to everybody? The omega is going to be in components now. Okay, so then basically what you're going to end up doing after that part is you're going to have to kind of do the transform one way and then transform it back to your XYZ. I mean, so unless, I mean, I've given it the answer in the end in the I and the little k with respect to those axes. If I hadn't asked you, like if you were just working this out, you could have defined it kind of. I've only asked you about what the dynamic loading of that shaft was, right? So you could have even left it in these, the X prime, Y prime, Z prime. That's an okay way to express an answer, right? But if you want to match the answers that I have here, and those make maybe a little bit more physical sense, right? If you have the X, Y, Z where it's, you know, along the shaft and then perpendicular to that shaft as well, because then you could start talking about normal and shear stresses and things like that. So basically, you're gonna have to get the omega into the new coordinate system as well. Okay, does that make okay sense to you there? So, and in this case, don't forget you have an alpha. So, you know, in this one, you probably want to, because you don't really have a, it's really a single axis rotation, right? You only have that one omega. It's not like one omega is making the other omega change direction. Okay, so for this case, when you do out your kind of your omega dot type of term, right, then you are going to have some, whatever your inertial tensor is for each one, but you are going to end up having omega dots, right, because you do have an alpha, right, because your alpha is right here, and you're also going to have to put that into components. Okay, does that make okay sense? Yeah, if you rotate into the proper one, right? What axes do you want it to be in, Aladad? Yeah, so those are what type of Oh. So what type of principal axes are those, Aladad? Yeah, so those are going to be principal axes for that rod. And does it make sense to you that this, remember how we talked a little bit about different shapes, but pretty much the sphere, it's also going to be principal axes for that sphere, right? Because pretty much any axes you choose just about are going to be principal axes for that sphere if it's going right through the G for it. Okay, and then if you're going to want to use your capital omega to be both of them here, so you're going to have, you know, whatever your total omega in both of those terms, right, crossed into your I, and then times the omega for the bar again, and those omegas are going to have components in both the z and the y axes there, and you're just adding the ones together, right, for the sphere and for the rod. Yeah, that's correct, right? And then what is the H? What is that HO dot going to be in the end? Is that a scalar, or what type of term is that? That's a vector, right? So then you've got a vector in the x prime, you know, so maybe we should have put, you know, that, hey, this is in the x prime, y prime, z prime, right, here, because I've rotated that thing around. Okay, and then what if I want it into, what I've asked you for really is the x, y, z, right? So if it's in the ijk that I've given you, now what do I have to do with this HO dot that I've expressed in the x prime, y prime, z prime? We use a transformation matrix to go back, right? So you can either use transformation matrix or you can use sines and cosines, right? But since you've got MATLAB at your disposal, then, you know, it may be easier for you to do the transformation matrix. Yeah, you may end up having, right, but you can have the, because your omega is going to have both a y prime and a z prime, so you're going to have like the y prime cross the z prime will give you an I and a z, and you know what I mean, Alec? So you could have, yeah, you can end up having a k cross k, and you can have a y cross y, and those will both be 0, but you can have a y cross z and a z cross y. Right, so Alec, does that make, yeah, give me a second, Aladad, I'll come back to yours. Yeah, so figure out what your total one. You can, I mean, you can always kind of do these things in parts as well as the things go. Okay, so you know, like you could potentially even like figure all this part out in the x prime, y prime, z prime, and then leave this part that we'll talk about in a second for Aladad, right? That we could leave in the other x, in the x prime. I'm sorry, in the x, y, and z. Okay, so for the final part, what Aladad was asking about is, remember, whenever we're going about just some arbitrary one like a point O or somewhere like this, then, and we're not doing it about G, right? We've worked several problems where we're doing it like about point G. Then if we want to look at kind of how dynamic reactions are going to be, then for most of these, right, so each of these masses that are out on the ends here, right, they're going to have, if I'm going in a circular path, what are the types of linear acceleration that the center mass can have? What are our two types of linear accelerations? Yeah, so we got normal and tangential, exactly. So we always have to think about those as we're working through, right? So what can end up happening now is if I look here and I'm doing the moments, right, and I'm worried about, I could be worried about the forces as well, right? But for these, my moments going, that normal is just going straight towards point O, right? So that's not going to have any type of effect on my moment. Okay? Does that make all right sense? But if I have some sort of an alpha, right, which in this case I do, right, I've got some sort of an alpha. So in this case, for those moments, right, then I'm going to have to worry about the tangential acceleration as well. So this R, you'd have to break it up into both of them, right? So if I'm adding that in, then what is the R? Let's call this body 1 and this body 2 over here, right? So what is my R from O to body, the CG, excuse me, of body 1, right? So to G1, and let's call that G2. Yep, so that's going to be B in the positive I hat, right? And then it's going to be crossed into M times the AG there is going to be B, right, times whatever that omega dot term is. Okay, and do you follow what I'm saying there? That's going to be, there's going to be a tangential acceleration there. Okay. Does everybody see that with the tangential acceleration? Because I have the omega of 30 increasing at a rate of 3 radians per second squared. Okay, and so that increase is going to be in the J direction. Okay, so this is for the sphere. Yeah, there will be a normal, but which direction is the normal one? So if I do my I, that's just, if I do here, it's the same, it's BI. So if this was the normal part of it, right? So what's BI, and then which direction does that go in? Yeah, it goes back in towards there, right? So this would be like a minus, and it's going to be a B omega squared times M, right? But that's going to be in the I direction as well. So I cross I is just 0. And in this case, they actually would also offset each other, Aladad, right? Because they're the same mass and they're the same distance away. Okay, so this is the sphere. And then when I do the rod, right, then it's, what's my R vector from O to G? Yep, so it's going to be minus B in the I hat, right? And then I've got to cross that into M times then my tangential acceleration of G2 there. Which direction is that going to be in? So the question is a tangential acceleration, right? So that thing's going around in a circular path. So we've got like a B omega dot, and which direction is that B omega dot in? It's minus J hat, right? Because if this thing's if we looked at it from the top, right? So the top's going around like this, and basically J is going here, right? And then this would be my X direction. So that would be X, and that would be my Y, and Z's coming up out of the board. Then the tangential one for the sphere would be going this way, and the tangential for the bar would be going that way. That was from the top one. Yeah, so Mule's asking, could we get rid of that by calculating the tensor matrix with respect to O? And yeah, you could, because we kind of talked about it a little bit last time. So depending on which one you're doing and how you're going about, really, if you think about what the parallel axis theorem talks about, it's m times b squared, right? Where b is that distance. It's just, you have to be super careful about doing that because usually you use a parallel axis theorem incorrectly. It gets to be difficult to apply that correctly. So usually I pretty much always recommend you do this full expression right here. Yeah, and then you add those together. I mean, sorry, you add the h terms together, Katie. Um, yeah, it's just multiplying them though, and so yeah, so two of these things. So I think you're saying you're going right, but it's not quite cross, right? You know what I mean? By it's really omega cross the I times omega again. So, did you follow that? Okay, good. And so I'm just thinking, I guess for this, now it's better to separate them out. I mean, for this one, actually, you get the same thing if you do it since they're the same distance away and they're the same mass that you could have just added them there as well. Both would work for this particular case. Okay, more questions. And basically, when I draw out my different forces and things here, I would do, if I'm doing my FBD KD, then I could do like a, I think you've seen me do this before with an FZ and then a double arrow for my MZ that's doing, and then I could do the same thing in the X, right? And I can do and I would free the body, right? So, but I'm just doing this shorthand just to make sure you guys have it set. Okay. We have not looked at 2 or 6 yet, Omar. Are there any more last questions about this one, though, first? In this case, we'll do O sometimes as a fixed axis or rotation, right? Which this one kind of is, but then since we've rotated around, it makes it a little bit more difficult. So you can use O in a bunch of different ways, but I only use it when I'm doing a single axis rotation and pretty much when we're doing those shafts with an eccentricity alidad. And then P is just any arbitrary point. So I can choose O there and then I can use either one if I want. So I could try to use parallel axis theorem, but in this case I would recommend just going through and doing the arbitrary one. So the top lines that you have, like 1 second, let me get the right. So I would say I use this, right? This would be the H, kind of basically about G, the H dot for G, and then this is like moving it over to point O, right? So this is basically saying that this is due to the change in angular momentum about G for this, plus the change in angular momentum of G for this. And then to get it over to point O, I use this term right there. Okay. Omar's asking about 2 and about 6. So which one do others want to start with? Okay. So Moulay voted first with 6. Okay. Is that what all you guys see now? So 6 up on the board for you? Okay. So, well, that's good because we were just talking um, about when to use the kind of the HO and the MO versus the MP. So this would be a case where I would actually do the sum of moments about O. Does that make okay sense to everybody? Okay, because I do just have that one single axis there, right? So when I do out my my FBD and my KD, right? So I would start out, I've got, kind of this guy going around like this, and then I've got this going up like that. So there's my sort of rendition there. So what do you think it means by the thrust bearing at A? Yeah, so that means, remember we talked a little bit about normally for the bearings, we're mostly talking about like a force going this way and a force going that way, right? And we didn't really give you, but let's just say that this is like an AX and this is an AY and Z's going up, right? So now is that okay? Is that a right-handed coordinate system, right? So I always have to make sure if I'm in charge of doing this that I have a right-hand coordinate system. So is that okay for that one?
Yeah.
Okay, so that's a right-handed one. So now what do I put up at B, at point B?
The reaction.
Yeah, so we're going to have the same basic ones, except now it's not the thrust bearing, right? So for that one, we don't really have to worry. So we can just do like a BX and a BY for this one. Okay, so it's not going to have to support basically like the weight, right? That thrust bearing, does that make sense to you that the AZ is really just going to have to counteract the weight of the thing? Is that okay with everybody? Okay, so now the other things that we could add on, just if we want to kind of figure out what's going on a little later, because we may need these points anyways, right? Because now we have that the whole thing does have some weight, right? So if we have that this is maybe a G1, this is G2, and this is G3, right? So we can do a little M3. And so do you understand what I'm doing here? I'm just kind of breaking these up into little parts there. So we're the kind of 6 foot long section is going to be my part 1. So this whole thing would be part 1, right? And then basically the second part there, right? This could be like our part 2. So that would be part 2. And then this other section going up there, kind of like that area is my part 3. Okay, and then typically what we've been doing is sort of drawing out just our, basically the overall thing here, wherever the CG of the whole thing is, we've just kind of drawn out some sort of arbitrary MAG and some sort of an HG dot. Okay, so sometimes those are helpful, sometimes they're not so much, especially if we're doing sum of moments about O. Okay, so now as we're looking at it, we can go through and do out our full expressions again, right? So in this case, we can say, well, what's my H dot and I'm going to do it about O now because I guess we have, it's really A and B, but it's a fixed axis. So if we look at our X, Y, Z, right, then that's going to be the first part, and then the second part that I'm going to do in here is just is my capital omega crossed into whatever my I about point A is, right, times my omega. Okay, does that make okay sense to everybody? And since I'm doing basically going to use parallel axis theorem now to get it about, this is my X, remember, this is my Y, and this is my Z axis. Since I'm going to do it about those specific axes, I don't have that R cross MA term, right? Because essentially I'm going to use, like I was saying, the parallel axis theorem. Okay, so this is going to be whatever our sum of moments about point A are going to equal. Okay, questions so far? Yeah, so what does I sub A denote? That is going to be my mass moment of inertia tensor about A. So remember we did a bunch of these different problems where we would have, you know, say something rotate, you know, maybe we had something here and then a couple different one, and then we had, I don't know, a sphere on the end of this guy, and then we had some sort of sphere on the end of this, and then we had a sphere on the end of that. And then we did, you know, we figured out what the mass moment of inertia tensor was down about this end so that we could figure out dynamic loads at A and at B. What's kind of almost the exact same thing, except for now it's turned 90 degrees. Okay. So is this X, Y, Z, is that principal axes?
No.
Yeah, it's not going to be principal axes. So, and then Alex asking, is that synonymous to where your frame is? Yeah. So you'd want to put your XYZ frame at A. Now I could also have decided to some moments about B, right? So if I had some moments about B, then I would put my axes up there, right? So this inertial tensor, right, this IA, right, is not going to be just principal axes, right? It's going to have some other terms in it as well. So in fact, let's look at this. So I have the XYZ. So let me, hold on for a second. I'm going to do this. So let's say we are now, let's break this out a little bit. So what's my omega going to be? What am I going to have for my omega?
The 10 rate.
Yeah, so that 10, which direction is that in?
Positive C.
Yeah, so I'm going to do like a 0, 0, 10, right? And then I'm going to cross that into, and now I have to look at all these guys, right? So I have, right, so I've got, sorry, I got to put minuses in front of all these. ZY and IZZ, right? And this is again, though, times 0, 0, and 10. Okay. So now I look, and which eyes do I have to worry about now? Somebody look for a second. What eyes do I have to be especially concerned about?
The ones in the third column.
Yeah, does that make sense to everybody? Because the only thing I'm going to multiply it by at all is going to be the 10. Right, so the only thing I'm really concerned about here is the ones in that third column, because that's all that's going to get multiplied, right, by this 10 right here. Okay, does that make sense to you? Because in the end, right, when I do this out, it's going to be this times this plus that times that plus that times that. So this is the only thing that I really have to worry about. Same thing, it's going to be this times that plus that times that, right? So those are both times 0, and then I have that times that, and then the same thing, that times that times that, and that times that. So the only ones I'm going to worry about is the third column there. Okay. Does that make okay sense to everybody?
Yeah. That ICZ, we wouldn't have to work it out for this case because it'll be crossed by that 10.
Yeah, you end up having a Z cross Z in the end, so it won't matter. That part will drop out. You're right. Okay, but that might not be as evident to everybody right away. Okay, is everybody else online okay with this so far too? Okay, so let's look if we have, do we think that IXZ is going to have a value, and do we think IYZ is going to have a value for this problem? Okay, so think for a second, and then in a minute I'll have you type in which of those two might be 0. So the question is IXZ 0 or is IYZ 0? Okay, so two think that XZ is 0. Anybody else? Okay, and I'll agree with that, right? Because IYZ is a plane of symmetry here. Okay? And you could actually go through and calculate it all out to find it, right? So if you remember what I typically did is I would find, we set these 3 different things here, right? These 3 different parts. So right here, I could say, well, that point's going to be 0, 0, 3, right? That's my CG for this bar 1, right? That I had done over here on the left. Then this point right here for basically my bar 2 would be 0 in the X, and then what is it in the Y?
1.
It's going to be 1, and then in the Z.
2.
Okay, does everybody see what I'm doing there? Okay, and then for the third one, right, we would have X again is 0, and then the Y amount is going to be 2, right, and then this amount's going to be 3. Okay, and then I'm going to use those coordinates to figure out what my I, Y, Z is going to be. Okay, questions so far? Okay, so now, is this term going to be 0?
No.
Okay, so what's going to make that be non-zero? What would cause the omega about the Z direction to change? Yeah, so Taylor's got it. It's that torque, right? So that moment's going to make that's going to make that thing change, right? So this H dot is essentially just going to be the same I that we had before, but now it's going to be times like omega dot X, omega dot Y, and omega dot Z, right? And in this case, it should kind of make sense to you that, well, omega dot x and omega dot y can't really change any, right? I'm not rotating about this axis at all, nor can I because of the bearings, right? Same thing for the y. So that's going to 0 and that's going to 0. So the only thing I have left is this omega dot z, right? And that's what I'm going to solve for up here. That's the angular acceleration of the shaft. Okay, any more questions there?
What would the left side of the equation look like?
So for the moments about A, well, so if you draw out your FBD, like what we've done over here, right? So if we're just asking for dynamic bearing reactions, then we say that these mg's are 0 essentially, right? So we had an mg3, an m2g, and an m1g, right? So if we're just looking for the dynamic ones, then we say that these are basically small compared to. But, you know, in the end, it's just going to be that if we're doing sum of forces, basically the AHZ is going to have to counteract those, right? But there's not going to end up, it ends up there's no forces in that direction, right? But then the left-hand side, because of, you know, what did I leave? Actually, what did I leave off my free body diagram in the end?
The reaction forces at A and B.
Well, I've got those, right? So that's over on the left. So I've got my reaction forces at A and B. But what did I forget to add?
I don't know.
Taylor, you just talked about something. What did I forget to add to my FBD? Yeah, I forgot to add the torque. Okay, so basically on the left-hand side of the equation is going to be from here, I'll have the torque, right? And then plus I'm going to have basically R cross my B terms, right? So that's going to be the left-hand side of the equation. So this right here is going to be that, right? Where the moments about point A, right? Because that's where I've done everything, are going to be the torque plus my R cross B. Yeah, so Mule is asking, why do we ignore the MGs? When we ask about the dynamic bearing reactions, then we're just looking to see, hey, how does the motion is this thing? How does the RPM affect what's going on to the bearings? Because doing the static stuff's easy enough, you know what I mean? So in this case, we're asking for the dynamic bearings. Does that make okay sense, Mule? And the other reason, usually those are so much smaller than what the dynamic ones are. So it does affect the results. It's kind of like how we did that too for impact stuff. You remember that the weight is generally so much smaller than the impulsive forces. Okay, and then don't forget, you also still are going to have to do some of the forces, right? Is going to equal mass times acceleration of the center, right? And in this case, you actually do have a force that's going to be, because this thing is not symmetrical about the axis AB, so you're going to have some sort of force. What type of acceleration is number 2 and number 3 going to have, linear wise?
Normal.
So it's going to have, and actually it'll even have a tangential, right? In the end. So you'd have to worry about both of those, right? Because it has a tangential because I have an omega dot. But in most of these cases, your normal accelerations are typically quite a bit larger than your tangential ones, okay? Because you have an omega squared term. Okay, more questions about this one? Okay, should we look at number 2 then?
Yeah.
Okay, so for this problem, right, we're going to start out and do same type of thing, right, where we notice that, hey, it's not asking me for 2 different positions, it'll have an impact or an impulse applied or anything like that. So if that's basically a ball and socket type of thing down at the end, then what types of reaction forces and moments can we have at the end? Yeah, so we can have an mg of this guy. And then what do I have down at point A? Yeah, so we've got an F of A, but what directions? So we can have a K.
I and J.
Yeah, so we'd actually just add them, put them all in there, right? So we've got an FZ. We can have our FY and an FX. So a ball and socket can do all 3 of those types of loads there, right? Because at that point, basically we don't, what does it constrain? Well, it'll let things rotate, right? So I can rotate around this way, I could rotate up and down that way, right? And so that would be about the X, and then I could even sort of tilt about the Y as well. So it would let any of those types of motions go, but it does keep point A right there. Do you know what I mean? So it lets the rotations go. So there's not a torque or a resisting moment, but there are all those forces on a ball and socket. Okay, so any other forces that are acting on, forces or moments that are acting on this thing?
No.
Okay. And then we've got, for our kinetic diagram, then typically, we've just been kind of doing some sort of MAG, and then, well, let's do the other one, because I've kind of done them both ways, and I don't know if this is quite as useful as doing it. Really maybe the better way to understand these is doing basically like a where this is my M A bar Y, and this is my H bar Y dot, and then let's see, we got same type of thing in the h bar x dot and m a bar x, and then we'll do our h bar dot z and m a bar z. Okay, so that's our kinetic diagram for how all the things are going there. Okay, so does that make right sense so far?
Yeah.
Okay, so now what we're going to do is let's sum up our, if we sum up the moments, right? What would be a good point to sum moments about? So the question is, what point do I want to sum my moments about? Yeah, so I'm going to agree with Nick that A is probably the best one, right? Because then none of those forces come into play, right? We could try to do it at G as well, right? But then we're going to have to, use all those different F's there. So if I sum moments about A, then I can do, again, with this whole deal where I have, well, what is H? Excuse me, I can do H of G dot about the local frame, plus now I can do my capital omega crossed into my should I do this square times my omega plus I see about an R from A to G crossed into M A G. Okay, does that make right sense to everybody? Okay, so, and this is going to be a little bit like some of the gyroscopic stuff that we're going to do in a little bit, right? So what do I end up having then in this term? So how do I want to set, what do you want to set your capital omega to? Can I make it just be the 20 radians per second?
No.
Correct. So can I make it be just omega 1?
Yeah.
Okay, so if I do that, right, then I can make this just be the omega 1, right, that's going around, and that's going to be in the z direction, right? And then I can plug in my I, and is that okay to make it just omega 1? Right? If I'm only rotating with the omega 1, does my inertial tensor of the disk change? Remember how we were talking about the previous one?
It shouldn't change.
Right, it won't change because it's the disk, right? So if the disk rotates, say 30 degrees, it's still going to look just the same to that XYZ axis that you see there as if it's sitting like it is right now. Does that make sense? It's still the same disk, right? And remember, we talked about how that's different than if I had a rectangle, because that is different than that in terms of the XYZ axes, right? Okay, so I can use that omega 1. Now, how about my H dot G term? Does that change over here with respect to that XYZ axis? Does that change?
Yeah.
Okay, so how does it change?
The omega 1 won't affect the 20 radians.
It does, but remember, I don't do that because if I'm using only the omega 1, then I don't worry about that alpha dot, because it's really about how the HG changes. And if I'm rotating around, like, let's say I'm standing on the edge here, right, looking out there, this vector is always pointing out away from me, right? This is the G vector that's in the Y direction, and that never changes, right? And with respect to me, because if I'm rotating around with it, it's always just looking kind of out. Looks like it's pointing out with respect to me. And if I look up, this H is always looking up as well. Does that make sense to you? Right, so that H with respect to how I'm looking at it doesn't change any. So if I set my omega there, that's going to 0. Okay, and a lot of that's because this is constant, right? Because that means I'm not going to have that 20 is not changing, so I don't have an omega dot y, and then this is constant as well, so that omega 1 in the z direction is not changing. Okay, and then if I look at the r cross mag term, if everything's constant there, which way is the linear acceleration of g pointing? Yeah, so it's just going to be normal, pointing right back through towards the center, right? So this term is going to go to 0, right? Because this is just normal only. And that's going to be basically, so j cross minus j equals 0 there. Okay, so the only thing you have left is this term, right? And the only unknown in that term is going to be your omega 1. This term here is just going to be your r cross mg. Which is in the minus k hat direction. Okay, so that's what that term's going to be.
Professor, quick question. Just for clarification, there's no tangential acceleration for this one because we have a constant angular velocity.
Correct.
For the omega 1.
Yeah, and both of them were constant, but yeah, the omega 1's the one that's important for the tangential acceleration.
Thanks.
Sure. Okay, so I'm going to run, and I'm going to stop the recording, and then I have to do all the processing, so that takes a little bit. So this should hopefully I'll be able to post this within about 45 minutes because it's got to go through and process whatever file it is online, and then I got to upload it to YouTube, and then I'll post it on Polylearn.
Thank you.
You're welcome. Let me see, which one was that? Nick, let me see. Let me go through and I'll see what I've got.